Welcome to our Science Brief. Today, we're looking at something tiny with a huge impact: biological particles. Think pollen, bacteria, fungal spores, and even tiny bits of plant matter floating in our atmosphere. These particles are now recognized as playing a significant role in how ice forms in clouds, which directly affects precipitation patterns and our climate. These biological particles are often called ice-nucleating particles, or INPs. Normally, pure water droplets in clouds can remain liquid down to about -38 degrees Celsius. But biological INPs are special. They can kickstart ice crystal formation at much warmer temperatures, sometimes between -13 and even 0 degrees Celsius. That's far more efficient than other atmospheric particles like mineral dust. Why does this matter? The formation of ice crystals is a critical step for most of the world's rainfall and snowfall. Because biological INPs are so good at this, they can significantly change cloud properties. This includes how long clouds last, how they reflect sunlight or trap heat, and their likelihood of producing precipitation. Recent research has found that the concentration of these biological INPs isn't constant. For example, in alpine areas, their levels can peak around midday as forests release them when temperatures rise. This daily rhythm can influence cloud formation and might even trigger intense rain or snow. Interestingly, rainfall itself can cause ecosystems to release more biological particles. This could create a feedback loop. More rain leads to more biological INPs, which then leads to more precipitation. Different types of particles also have different roles. Some bacteria-sized particles are strongly linked to ice formation when local forests are the main source, while larger fungal spores and pollen fragments might become more important during dust events. The influence of these biological INPs on clouds and precipitation has major implications for our understanding of Earth's climate. Clouds can both cool the planet by reflecting sunlight and warm it by trapping heat. The precise effect depends on cloud properties, which, as we've seen, are influenced by INPs. Current meteorological and climate models often don't fully account for these biological particles or their cyclical nature. This omission means our models might be missing important factors that drive precipitation and modulate clouds, potentially affecting the accuracy of climate forecasts. As the climate warms, we expect to see more biological particles in the atmosphere due to changes in vegetation and shrinking sea ice, making their inclusion in models even more critical. This isn't just a localized phenomenon. Research in the Arctic, a region warming much faster than the rest of the globe, shows a strong connection. In the Arctic summer, over 90% of particles initiating ice at warmer temperatures, as high as -15 degrees Celsius, are biological. Even in winter, this proportion is substantial, ranging from 50% to 85%. As the Arctic continues to warm and more land is exposed, levels of these particles are likely to increase. Studies over oceans like the North Pacific and Arctic Ocean also suggest that marine life contributes to atmospheric bioaerosols that can act as INPs, especially during periods of high biological activity. Despite this growing understanding, challenges remain. Accurately simulating the concentrations and variability of biological INPs in large-scale climate models is difficult. This requires a better grasp of their sources, how they become airborne, their transport through the atmosphere, and their precise ice-nucleating efficiencies. Future research will focus on developing new detection techniques and improving these simulation models. We also need more comprehensive investigations into the characteristics of atmospheric biological INPs across diverse ecosystems. In summary, biological particles are emerging as crucial players in atmospheric processes. Their unique ability to initiate ice formation at relatively warm temperatures significantly influences clouds and precipitation, and consequently, regional and global climate. Continued research and integrating this knowledge into climate models are essential for accurately predicting our future weather and climate change. Thank you for listening.